Reinforcement learning, RL, is a branch of machine learning that focuses on training agents to make decisions in an environment to maximize a reward signal. The general pipeline of an RL setting involves an agent interacting with an environment, receiving feedback in the form of a reward signal, and updating its policy based on this feedback to maximize the long-term reward. Key concepts include the environment, policy, and the balance between exploration and exploitation. The Markov decision process, MDP, framework gathers these components as S, A, T, R, gamma, where S is the state, A is the action, T is the transition function, R is the reward function, and gamma is the discount factor. The discount factor determines how much the agent cares about rewards in the immediate future compared to those in the distant future. To make the setting more suitable for real-case scenarios, the expected return of GT, also called the value function Vt, is considered. Solving the MDP consists of maximizing the value function, which is a difficult problem known as the infinite horizon problem. The Bellman equation trick is introduced to address this, recursively approximating the return G and the value V. Various algorithms and techniques have been proposed to solve reinforcement learning problems, including QLearning, DQN, Reinforce, DDPG, TD3, and PPO. These algorithms are categorized as value-based, policy-based, model-based, or model-free, and can be on-policy or off-policy. The QLearning algorithm is a TDBASED model that belongs to the tabular RL model family, updating the model's policy based on the value function V and not requiring a model of the environment. Other algorithms, such as SARSA and Monte Carlo tree search, will also be discussed. These algorithms are either TDBASED or Monte Carlo based, and rarely rely on dynamic programming. QLearning, a fundamental algorithm in reinforcement learning, evaluates the quality of state-action pairs using a Q function, defined as the expected return when taking action in state S and following policy pi thereafter. The Q function is related to the value function V through mathematical expectation. QLearning uses a Q-table to store Q values, updated based on observed rewards and estimated future values using equation 7. Algorithm 1 outlines the QLearning procedure, which iteratively updates the Q-table using the epsilon-greedy method. However, QLearning has limitations in environments with continuous states and actions. Deep QLearning, DQN, addresses this by using neural networks to store Q values. The DQN architecture involves two successive designs, with the second one improving upon the first. The updated DQN architecture introduces a replay memory and a target network to mitigate correlation between successive experiences and the moving target problem. The replay memory stores transitions and randomly samples them for learning, ensuring EDE-like data. The target network calculates the target Q value, making the model more robust and stable. The inner workings of the DQN architecture are illustrated in Figure 3 and Algorithm 2. The learning episodes begin by initializing the two networks' parameters, and the agent gives an action based on the state provided. The transition is stored in the replay memory, and the Q network is updated via the mean square error to minimize the loss between the predicted Q and the real one. However, DQN has limitations, mainly due to the categorical way of generating actions, making it unsuitable for continuous action settings. Policy gradient, PG, algorithms propose a direct way of doing reinforcement learning with neural networks, having a solid mathematical basis and directly mapping states to actions via a learnable, differentiable function approximator. The gradient loss in PG algorithms is directly proportional to the policy, intuitively. The policy gradient theorem is utilized to derive an expression for the gradient of the objective function, enabling direct updates of the agent's parameters based on its policy. This is achieved by applying the log derivative trick, transforming the expectation of the reward into a form optimized using gradient ascent. The resulting expression, nabla theta j, pd, equals e, n array summation nabla theta log, pd, at, saint, r, tau, tt equals 0, enables training reinforcement learning agents in continuous setting environments. The reinforce algorithm implements the policy gradient theorem, using a neural network to map states to actions optimally. However, it suffers from noisy estimates of the gradient due to unclear credit assignment. Actor-critic architectures, such as the Deep Deterministic Policy Gradient (DDPG) algorithm, address this limitation by utilizing both policy and value functions for learning optimal strategies. DDPG operates in high-dimensional continuous state and action spaces, using a deterministic policy function to map states to actions directly. The critic learns by minimizing the mean-squared error loss between the predicted Q-value and the actual one. The DDPG algorithm combines the advantages of policy gradient methods and Q-learning, using a critic to predict Q-values and an actor to select actions. The critic is trained using a replay memory and target network, similar to the Deep Q network (DQN) model. Action selection is executed according to the equation at equals mu street thm plus ent, where ent is a noise signal added to the policy function to force stochastic behavior. However, DDPG has limitations, including instability and high sensitivity to hyperparameter tuning, which can lead to convergence to poor solutions or divergence in tasks requiring more exploration. The twin-delayed deep deterministic (TD3) policy gradient model addresses these limitations by maintaining a pair of critics, Q1 and Q2, along with a single actor, reducing the overestimation bias and improving performance. The twin-delayed deep deterministic (TD3) policy gradient algorithm is a variant of the deep deterministic policy gradient (DDPG) model, which aims to mitigate the overestimation bias inherent in Q-learning in deep Q networks (DQN). TD3 uses two critic networks to approximate the Q-value, updating the policy less frequently than the critic networks. This approach is inspired by double Q-learning and double DQN, utilizing two networks for improved Q-value approximation. The algorithm iteratively selects actions with exploration noise, observes rewards and new states, and stores transitions in a replay memory. A mini-batch of transitions is sampled, and the policy is updated using the deterministic policy gradient. The critics are updated using the clipped double Q-learning target, combining the minimum of the two Q-values. The target networks are updated using Polyak averaging. However, TD3 has limitations, including manual exploration through Gaussian noise and computational heaviness due to the use of 6 networks. Additionally, TD3 is only suitable for continuous space environments. In contrast, the Proximal Policy Optimization (PPO) algorithm uses a stochastic policy, inherently handling exploration automatically. PPO learns online, collecting mini batches of experience while interacting with the environment, and updates its policy using a trust region approach. This approach ensures that policy updates do not deviate too far from the previous policy, resulting in smoother training and less variance. PPO was developed for ease of implementation, sample efficiency, and ease of tuning, and has shown impressive performance compared to previous models. The PPO algorithm is outlined in Algorithm 6, which initializes policy parameters θ0 and value function parameters φ0. It then collects a set of trajectories, computes rewards to go, and computes the advantage estimates. The policy is updated by maximizing the PPO clip objective, which involves computing the clipped surrogate loss. The value function is fitted via mean-squared error, MSE, loss. Despite being a state-of-the-art algorithm, PPO's limitations are yet to be fully explored. It has been used to fine-tune the ChatGPT model and is still the main algorithm used at OpenAI. In conclusion, the choice of reinforcement learning (RL) algorithm depends on the specific characteristics of the problem at hand and the trade-offs between sample efficiency, stability, and convergence speed. Model-based algorithms are more sample efficient but may be less robust, while value-based algorithms are widely used but may suffer from instability or divergence. Policy-based algorithms are generally more stable but may be slower to converge. This review aims to provide a comprehensive overview of RL, including its key concepts, techniques, and algorithms, as well as its challenges and limitations. Reinforcement learning has been extensively applied across various domains, including games, healthcare, finance, robotics, and supply chain management, with numerous surveys and reviews published in recent years. Research has demonstrated the effectiveness of reinforcement learning in these domains, with applications in games, 3, 4, healthcare, 5, 6, 7, finance, 8, robotics, 9, 10, 11, and supply chain management, 12, 13. The development of reinforcement learning algorithms has been instrumental in achieving these applications. Watkins, 18, introduced Q-learning, a fundamental concept in reinforcement learning, while MNIH et al. 19, applied deep reinforcement learning to play Atari games. Sutton et al. 20, developed policy gradient methods for reinforcement learning with function approximation, and Lillicrap et al. 21, presented continuous control with deep reinforcement learning. Function approximation error in actor-critic methods was addressed by Fujimoto et al. 22, and proximal policy optimization algorithms were developed by Schulman et al. 23. Liu, 24, proved the convergence of Q-learning, and Tobin et al. 25, reviewed deep learning in multimedia healthcare applications. Chen et al. 26, improved deep QE networks for user-side battery energy storage charging and discharging strategy. Other notable developments include the deep reinforcement learning-based DQN agent algorithm for visual object tracking, 27, deep Q-learning for dynamic resource allocation, 28, and deep reinforcement learning with double Q-learning, 29. Actor-critic algorithms were developed by Konda and Seetsiklis, 30. Matharon et al. 32, analyzed the problem with DDPG, and Schulman et al. 33, developed trust region policy optimization. These advancements highlight the potential of reinforcement learning for solving complex problems across various domains.